Hello, thanks for dropping by my presentation. I'm very happy to share with you my work that set the stage for my research group as a faculty member at your school. I encourage you to check out my poster, which summarize key points of this talk. So today I'm going to tell you about how I have been using computer simulations to help design biomimetic materials from bottom-up approaches such as self and directed assembly. Uh, this work has been inspired and supported by a lot of amazing people, which I show you here, and I can thank enough the support from them, also from the funding agencies throughout the years. The motivation of my work comes from the fact that biomimetic materials have been offering a lot of promising solutions to the challenges we are facing as the whole. I'm showing you a couple examples where these kind of materials not only look but also function like biological systems that provide transformative approaches for healthcare, environment, and energy applications. For example, how we can engineer soft electronics that talk to our brains, or the new way to dissolve plastic waste, or the new way to um, fabricate structural batteries used for robotics. What we have been seeing here is that we can combine the functionalities and compatibility from biological building blocks with synthetic building blocks like polymers, nanoparticles, and colloids. And it really shaping up an emerging paradigm because now we can have the advantage of two different worlds where we can provide both functionalities and strength and sensors and actuators in the whole um, nano devices and materials. And the key here is to our ability to understand and to control over the interactions between very different building blocks at the nanoscale, how to organize them in a large number into the structures of the device with the given task. Of course, the challenges to this approach coming from different aspects. Here are a couple of challenges that research groups have been trying to address. For example, what kind of morphologies we want to assemble from bottom up, how those nanobuilding blocks interact with each other, and how to guide them into desirable structures, how to make those structures not only look but also function like biological matter in the sense that they can respond to change in temperatures, light, and pH in a controlled fashion. That's where my research come in play. Over the years, I have been using multi-scale modeling, computer simulations, and big data analysis to help experimentalists and theorists design colloids, polymers, quantum dots to uh, engineer different kind of nanostructures that used in a wide variety of applications that shown in this slide. The output of this study are the design rules that narrow down the design space for those building blocks. But more importantly, is to provide fundamental knowledge of what's going on at the nanoscale so that we can expand further what has been achieved in current experiment. What makes my research stand out from many others entering the field is the fact that I involved into the development of new tools that allowed not myself but other research groups perform simulations much faster and more reliable compared to before. I'm showing you in here this slide. My work has been used to accelerate the performance of the simulation across the board for different kind of systems, with speed up ranging from 5 times to 20 times compared to the case that we don't use graphics processing units, GPUs. And with this acceleration in speed, we can hope that we can address much larger length and time scales with the facilities that we can access to. And with this work, I have been awarded by the R&D 100 organizations as a member of LAMP's development. LAMP is a very well-known software package in the field of chemical engineering and material science, used for computer-aided design. Not only making simulations faster, but I'm also able to develop and improve and implement a lot of algorithms that help simulations, giving reliable predictions. This is very important for the computer-aided design problems, because otherwise we cannot trust anything if we don't know that we assemble the system or the phase space accurately and reliably. So in these presentations, I'm going to show you how I applied those advanced computational tools that I have developed to understand and to predict the design rules to engineer hybrid nanobiosystems, in this case, protein and nanoparticles and protein and random copolymers. I will show you more for the second systems in the poster that you can take a look closely, and we can discuss further at the end of these presentations. Here I only want to focus in one of very interesting examples where we mix nanoparticles with proteins to assemble biomimicking structures that work like bioreactors. This fascinating work initiated by my collaboration with my collaborator Nick Otop at U of Michigan. What Nick and his group reported is the very interesting behavior when you mix nanoparticles and cytochrome C, which is very small size, around 5 nanometers. These two kind of building blocks having the same charges, but then they can assemble into spherical clusters, as shown in this figure in the middle with very sharp size distributions, which is much bigger than the size of the individual particles. Interestingly, those clusters do not coalesce or merge, even when they are highly concentrated, as expected when clusters should form really big to minimize their surface tensions. And the question we want to address in this study is that how we can rationalize, understand what's govern the final size of those clusters, and from that to predict how to control the final size of such kind of systems. So we start the very classical descriptions for these systems using DLVO theory. You can see given two particles Qi and Qj charges in the solvent of gradual constant epsilon r. This theory gives us three contributions to the interaction between two particles as shown in here. I want to focus on Aij being the repulsion strength between two particles, which is a function of the charge, Qi and Qj and epsilon r. And the plot on the right show you how we increase convert a short-range attractive forces into a purely repulsive interaction between those two particles because they have the same charge, same sign charge. This model, however, conformed to the classical nucleation theory, which states that beyond a critical size marked by the triangle here in this plot, all the particles are favored to form infinite clusters to minimize surface tensions, which is not observed in Nikodov's experiment data. So how we can understand or rationalize this within this ERVL framework? So I go back to the original assembly process and observe that when the particles start to clump together and form clusters, we see an emergence of the interface between the cluster and the solvent around it. And up to a point when the electric constants of the clusters get reduced because of accumulation of the charge inside those clusters, causing a mismatch between epsilon inside and outside, which repel all the particles away from the clusters. And that's where the cluster acquire their final size. So to capture those effects, what I did is to modify AIJs as a function of where the particle reside. Either they are in same cluster, A intra, or they are coming from different clusters captured by A inter. And in my model, I just use a single scalar parameter S to capture how strong the particles from different clusters repel or interact with each other as a function of the size of those clusters. And with that model, I have been able to capture the dynamics of the assembly process going from initial distributions into a final size with the final peak at the rate curve showing here. And in this case, we will also capture the fact that those clusters do not coalesce, even they are very high concentrated as observed in experiment. The model will be able to predict how to control the cluster size. In this case, we can just increase the ionic strength. Technically, effectively, what it means is that we can decrease the Coulombic repulsion strength between those particles. And these predictions tell us how to tune Vmax, the maximum size of the clusters, towards smaller value if we increase the ionic strength. And these predictions has been confirmed by experiment by Nikodov's group. So what this study tells us is that using modeling and simulation, I have shown you how our model is a significant improvement upon the classical nucleation theory by predicting optimal cluster size. And this model bring our systems under investigation to have the similar physics observed in other biological systems. For example, for the formation of the viral capsids or the finite thickness of the microtubules or even geometrically frustrated assemblage, which also reported to have a similar optimal characteristic size. So this to summarize the whole theme of my research, and which I want to develop my research group towards, is to combine the power of modeling, simulations, and data analysis to provide experimentalists and theories not only the physical insight into the nanoscale interaction between nano and biosystems, but also to offer some design rules in terms of what kind of parameters we should synthesize building blocks so that they can assemble themselves into material that not only look but also work like biological systems. And these will all offer a lot of opportunities for us to engineer building blocks and materials and devices that solve global challenges in healthcare, environment, and energy. So I want to wrap things up here, and I'm very happy to answer your questions. And thanks again for dropping by and spend time with my presentations.